Ms. Newton went for a ride on her horse in a field by the lake. She wanted to get to the small island that was 5 miles down the shore of the lake and 3 miles away from the shore, perpendicular. Her horse can trot along the shore at a pace of 8 miles per hour and can swim at a pace of 2 miles per hour. Find the least amount of time, so minimize, for Ms. Newton and her horse to reach the island. And we also want to know how far from their starting point should they enter the water and swim. So starting point, here's the island over here. So this is the lake and this is the shore. 5 miles along the shore, and the island is 3 miles perpendicular away from the shore. So she starts trotting along this way, and at some point, she and the horse get into the water and head out to the island. So let's label some things. So we're actually interested in how far along here before she heads out. Even though this is not what's asked, I'm labeling this as X because I know I'm going to need to use the Pythagorean theorem and I want to have a simple expression rather than a complicated one. So let's call that distance X. If the whole distance is 5, then this distance must be 5 minus X. So that's 5 minus X to here. All right. And then this is 3 miles. We know that distance. And this distance is going to be important because that's the distance that she and the horse are swimming. So we have a right triangle here. So side squared plus other side squared equals hypotenuse squared. So 3 squared plus x squared equals hypotenuse squared. So if I take the square root and I only need the positive because it's a distance, that will be this distance here. So we're actually trying to minimize time. So we need an equation for time. So notice distance equals rate times time. And if we solve that for time, we get divide by r. So time equals distance divided by rate. So I'll write capital T for time is going to be the time on land plus the time in the water. So the time on land would be the distance on land, which is 5 minus x, divided by the rate that they move on the land. So let's see. On the shore on land, we go 8 miles an hour. That's the rate. So divide by 8. And then we'll add the time in the water. So the distance in the water is the square root here. So square root of 3 squared, which is 9, plus x squared divided by the rate they swim. So let's find that. Pace rate, 2 miles per hour in the water. So divided by 2. So that's time. And it's already as a function of x because I wrote my expression here as 5 minus x, and I wrote this as a function of x. So we didn't need to do more work to get only one variable. So we have a time as a function of x, which is this distance between the perpendicular point and where she jumped in the water. So let's pause before we find the derivative and figure out what we have for the domain. So this entire distance from where they start to this point along the shore that's perpendicular to the island is 5 miles, and this is part of that 5 miles. So she could travel the entire distance along the land, which would make all of this x. So x could equal 5, and x could equal 0, like she could trot all the way to here and then only swim this perpendicular distance. So the domain is x is between 0 and 5, and it includes the boundary, so it's a closed interval. So at the end, we're not going to have to check to determine whether we found a maximum or a minimum. So now we're ready to take the derivative. So let me do one more step before we actually take the derivative. Let's split this into 2 fractions. So this would be 5 over 8 minus x over 8. And I'll rewrite this with, let's see, I will rewrite this with 1/2 in front, and a square root can be written as a radical exponent, so 1/2. So the derivative of a constant is 0. This is -1/8. The derivative of x is 1. So 1/8. All right, now we're going to use the chain rule. So I have the 1/2 as the coefficient. I bring down the exponent, that's 1/2. I leave the inside function alone for the chain rule, decrease the exponent by 1, multiply by the derivative of the inside. The derivative of 9 is 0. The derivative of x squared is 2x. That's the derivative. I do want to simplify this a bit. So also ultimately I'm going to set it equal to 0 to find the critical values. So 1/2 times 2 is 1. So that leaves me with 1/2 x times 9 plus x squared to the -1/2. So let's move the 1/8 to the other side by adding. So we have 1/8 is equal to 1/2. Now let me rewrite this without the negative exponent. So x is in the numerator, and 9 plus x squared to the positive 1/2 is in the denominator. Now I'm going to multiply both sides by 9 plus x squared to the 1/2 to get this radical expression out of the denominator. So that gives me 1/8 times 9 plus x squared to the 1/2. So that took care of that, is equal to 1/2 x. Now, I'd really love it if I didn't have that radical exponent. I think I'm going to multiply both sides by 8 to get the coefficients on the same side. It's not strictly necessary to do it at this point, but to be easier. So 9 plus x squared to the 1/2. 8 divided by 2 is 4. And now let's square both sides, and that will get rid of my square root or radical exponent. So 9 plus x squared is equal to 4 squared is 16. X squared. Subtract x squared, that gives me 9 equals 15. X squared. Divide by 15. 9 over 15 is equal to x squared. Take the square root of both sides. That gives me x is equal to plus or minus 0.77. And those are my two critical values. I'm ready to make my table. So I have my x values and my time values. And again, please remember that you're plugging it into your original time function, whichever one you think is the most simplified, which you could use either one of these. So the lower bound of the domain is 0. The negative critical value is outside of the domain. 0.77 is in the domain. And then we have the upper bound of the domain. And we plug each of those into the original time function. So a lot of calculator work. And we plug in 0, we get 2.13. We plug in 0.77 and we get 2.08. And we plug in 5 and we get 2.92. And we were looking for the minimum time. So this is the minimum. And reminder, we had a closed interval, so we don't have to check that we really got a minimum. The lowest one is going to be the minimum. So the minimum time is 2.08 hours because our units for rate were miles per hour. So hours are the time units. And Now, let's make sure we're answering the question. How far from their starting point should they enter the water? So x is 0.77. So how far from the starting point? That should be 5 minus x. So 5 minus x is 5 minus 0.77. So that would be 4.23. And what's this unit in? All of our distance units were in miles, so this is miles from the start.